So the last speaker of the session is Jinhua Zhao, and he is a professor of city and transportation planning. He founded the MIT Mobility Initiative, which coalesces the Institute's efforts on transportation research, education, entrepreneurship, and engagement. He also directs the JTL Urban Mobility Lab and Transit Lab, leading long-term collaborations with transportation authorities and operators worldwide. And he's co-founder and chief scientist of a recent spin-out Tram.global, which is a mobility decarbonization venture. So please, let's welcome Jinhua.
Thank you, Jeff and Vivian, for organizing the event. I'm still digesting the talk by Sarah, Abigail, and Priya. I'm a city planner, right? I work on transportation. So at the beginning, I was still like, there's such a contrast between the three prior presentations, which most talk about natural system, the physical system, while in city planning and transportation, we talk about a hybrid between a human system and a physical system. If you think about most of urban infrastructures, right? Many of the infrastructures, by and large, are physical system. But transportation, there are tracks, the road, the bridges. But half of the system are actually the human beings. We are the one who drive the cars, we're the one making decision, do I bike today, or the user of the system, et cetera. So I try to offer a contrast between the two. But then after listening to the three talks, I really find that there's surprisingly a lot of similarities and a lot of common issues. So I try to distill some of them. I'm doing this on the fly, so I try to offer some of that. For example, Sarah mentioned about this long tail, this rare occasion, the representation issue. In city planning, we have the very similar question there. Abigail talked about the multi-scale, where you have a lower scale, much more detailed model about how to embed it into the upper scale discussion. We have almost exact analogy in transportation system or urban system. And Priya offered this whole framework of how machine learning can apply to different parts of the system. I don't know if you remember her chart. I'm just the top right corner transportation that in her framework there, right? So really nice flow. I'm really surprised about the coherency actually in the panel there, right? So I will try to talk about a few areas that AI can help in decarbonization, but also maybe I should start from one area it cannot, right? Let me give you an example. Throughout human history, we invented a whole bunch of technologies that help us from move A to B. But actually, MIT contributed to many of this, right? So at this speed, you would think our transportation system must be in the paradise. We have a very efficient, equitable, and inclusive system. But of course, if you live in Boston, you see that's far from the case, right? That's nothing surprising. You see this. But also, this is not just unique to Boston. This is in China. You see similar situation there, right? Actually, the whole world actually moving more toward this type of system there, right? But I would say that a few of you probably come to Beijing, the same city, 40 years ago. This is a picture in 1982. If I ask you what you see in this picture, you see there's a bicyclist, there's pedestrians, there's public transit. By the way, all electrified public transit, right? For that aspect, MBTA is struggling on how to electrify buses, right? How do you call this picture in this modern planning jargon? You call this sustainable transportation, active transportation, clean transportation, active transportation. We have all this beautiful word describing the paradigm that transportation planners really want. But that's 40 years ago. And Beijing as a city strives itself to move away from this to here, right? So I would say that as a discipline, we're utterly confused, right? So what is even success? Right? I do want to raise the question, that's a case where AI wouldn't be able to help. That's really our decision on this. And in computer science, we talk about alignment problem between what human preference and a machine preference. But the question in transportation is we couldn't align ourselves in what do we mean by human preference in transportation. That's really the first thing I want to mention. Right? The second one is interval decarbonization. There are really two camps of thought. Even with MIT, we debate that all the time. The first one is let's electrify the car or put hydrogen or et cetera. Right? This is really a more technology-oriented solution. The issue is, car's a problem, let's improve the car, right? But there's really a distinct view on this, which says car itself is the problem. It's not to improve the car, let's get rid of the car, right? Let's have other mode thing. This is the behavior change part, right? Here, of course, there's a lot of debate and commonality between the two. But here, really, what defines the future of mobility? I would say that there are really two parts. One is the behavior part, that's the humanist side of it, and there's other computation where we can engage in designing new technology, optimize our system, etc. Right? Here, on the behavior side, for example, my research often asks, is travel a social issue, phenomena? Is it emotional phenomena? Is time absolute? Is perceptual problem? You can actually ask this question by actually looking at many of the business decisions. For example, EV range anxiety, that's what Tesla's worried about. Ride-sharing pricing issue, that's what Uber and Lyft are worried about. AV adoption issue, that's what kind of Waymo or Zook, et cetera, about. Congestion charting, that's what we mass DOTs worry about, right? You can translate many of the business decisions into a behavior angle, right? In behavior science, a lot of questions, we exact answers try to address those questions. Then on the computational side, AI has been applied to transportation for decades, right? For all these different aspects. Actually, Priya mentioned a few of this, maintenance example, for example, demand prediction, et cetera, on this. Right? But here, in my research, I really want to try to bring this behavior thinking, asking questions like emotional, social, perceptual, and the transportation technology together. Right? That's, I think, what makes the research quite interesting, and use the computation as a foundational layer to support many of the integration here. So I set up the mobility initiative, as Jeff mentioned. I really bring the different people together across MIT. For that, I also surprised that I discovered, actually, more than 70 professors at MIT actually study transportation very seriously. This, right? Even I've been here for 10 years as a professor, I keep discovering people actually working in the field. For example, Priya, I will invite you to this as well as one member of the process. Right? Okay, so let me get to a few areas. I do think AI can help with the urban mobility. I put them into the 5 categories: representation, prediction, explanation, control, and creation. If you match this with what Priya's presented, actually there's quite a mapping between when we use a different word, different sequence, but actually very much a similar kind of structure in this. Into the representation, see, can we have a multi-channel view of cities? Into prediction, can we really deal with unstructured data, do a better demand prediction? Can we use AI for really scientific discovery? Can we improve the bus control system? Can we generate more interesting plans? Those are the 5 areas. Given the time, we'll just show a few examples. On prediction, right? This is with the help the student work from Qingyi and Dingyi. So one fundamental question in transportation planning is, if you, actually, by the way, I asked, how many come here today by public transit? A few. How many walk and cycled? The rest, you take cars, I assume, or school boarding or something. We're saying that this choice is one of the really most fundamental choice. That then leads to different mode choice, different traffic condition, different energy consumption, CO2 emission, right? So this is the classic question in transportation. So often in the field, we will predict this choice. We think, well, what a factor influences them, right? The classic setup here is the travel time, travel cost, your income level, the distance, purpose, etc. That's kind of a classic set of things, right? In this set of attributes, we call this structured data, right? Kind of what you can put in relation to the database. That's type, right? Then another category is called attitude, preference, and habits. That's what's your view about climate, for example? How are you environmentally conscious? Yeah? Are you influenced by other people's view of your behaviors, as they said, for kind of attitudinal one. The third category is the so-called built environment, right? So how you travel is not only your decision, actually much of your decision within an architecture that's determined by other people. For example, do we have a reliable MBTA service or not, right? That's part of the environment. Do you have a pedestrian-friendly walking path, right? So the built environment. Let me just focus on this part for now. In this part, how to deal with built environment, there are really 2 different ways to deal with it. The first one we call handcrafted feature. This is also generic manual machine learning context, is you conceptually design what factor you want to distill. So if you're given a satellite image, you calculate the density of the people in this area. And typically say the higher the density, the more likely to use walking and cycling, for example, right? The diversity, the design, the destination accessibility, et cetera, right? But another way to look at it is just saying, what if we just use the image as itself? Right, the built environment as itself. And it turns out the built environment can give us a lot of information, can predict the various socioeconomic indicators, can describe many of these functions there, right? So here, for a long time in transportation planning, we don't know how to deal with these pictures, et cetera, right? That's very similar to cross-domain biodiversity, the climate change, etc. Now, we are able, just as many disciplines, is able to take those unstructured data and integrate it with the structured, more numerical data and do prediction. Right? Here, you can show that by combining the two effectively, you can really improve the prediction efficiency. The other thing I do want to mention is the image-only prediction is also powerful because in much of the world, you just don't have any meaningful socioeconomic data here, right? In US, we have a good census system, et cetera, but much of, say, Africa, you just don't have many of that. In the image is not predict as good, but at least you have some baseline to work with. The other thing is not only for prediction, it turns out that this model can also generate. This example where to the right, this is downtown Chicago, and to the left is the south of Chicago, right? You have the two extremes, and this model is actually allow you to generate the thing in between, right? So you can have a different degree of hybrid, and depending on the building environment, you can actually predict their mode share for car, active travel, and transit, et cetera. Right? So that's the first example. The second example is more on the control side, is taking actions, right? And for that, many of you here by taking public transit, you're familiar with this case of the bus bunching, right? Buses just never come, so when they come in three, right? So this is often the problem there, right? But so this is the illustration of this. But what makes things even worse in the last few years is there's almost a pandemic issue on the service reliability because of driver shortage and the driver absenteeism. If you talk to, say, Chicago Transit Authority or MBTA or WMATA in DC, et cetera, they often find that we just couldn't find enough drivers to work, right? And for those who do work for Chicago, some of them, they just don't show up on the day, right? This becomes a massive problem. It turns out, for example, city in Chicago, they promise a certain amount of service on the timetable. They actually only deliver 84% of them. I mean, that's shockingly bad. I mean, 16% of them just not delivered because I don't have driver on this, right? Then think about it. Suppose you have a 10 minutes headway. The second bus, the driver says, I'm not coming. Then suddenly become 20 minutes headway. And from people only that will suffer a lot, right? So that's the situation. We try to say, can we really improve some of the service reliability through a reinforced learning-based bus control process here to be robust against the uncertainty in driver absenteeism, demand uncertainty, and also the inaccurate information there. So that's what we did in Chicago. This bus 81 goes from here to all the way to the Michigan Lake. This is the terminal where you have the bus, and this is the garage. So what we've been doing is working with Chicago, develop a RL-based control strategy, but then work with them to actually deploy this system, right? Here, I do want to mention one area that's distinct from the pure natural system. Because whenever what MIT research says, okay, hold the bus for 2 minutes so that you balance the headway, for example, that's what AR says. But in the end of the day, is the people have to execute it, right? Later find that often the bus driver will say he totally ignored it. Who are you come here lecture me to what to do here? Right. So that's where human behavior has to be part of the loop. That's where it makes things, I think, challenging, but also interesting here. All right. So let me, oh yeah, by the way, actually, the choice of 81 is not our initial choice. We analyze unreliability. We'll try to find the most high demand but unreliable service and to do the test. But CTA advice against the initial choice says that may be true for your analysis. But if you work with that garage, that drivers, they're not going to work with you. It doesn't matter how good your math is. So they recommended us a different garage, a different bus stop, said those drivers are much more open-minded. They're more likely to respect whatever RL says you should do. So this type of knowledge, I mean, we have no clue. So only because we collaborate with the local partner that we know, that's also another important distinction there. Right? So with this type of control, I mean, this is the human in the loop. We have this rule-based control. You have RL-based control. Then some people make a judgment. But in the end of the day, this decision by the RL, you cannot just assume it's being implemented. It gets to a supervisor. Supervisor has to talk to the driver. In each of the chain, you will find some incompliance, right? Some incompliance, maybe even good compliance. But anyway, this is not a direct translation. Through this process, a lot of kind of variations in that. All right. So then, what do we? So these are our students in the different control room, etc., to make this happen. But then let me show you the result. Right. The first one is through this control, just by balancing between different buses, we're not adding new buses or new bus drivers. We're able to reduce the exit waiting time by 30%. This is actually quite a bit of a change, right? A simple thing, just make the headwind more even with each other. It's just a simple logic there, right? Of course, the RL can anticipate a little bit more downstream one, more than the heuristic can do. But this is, we reported this to CTA, this is this massive impact, right? Because for them to achieve a 30% reduction in exit waiting time, if they do it in the traditional way, they have to buy more buses, train more drivers. That would take years to happen if they have money at all, which they don't today, right? So that's why here. It also reduces the overcrowding, reduces the cycle time, et cetera. So in terms of the performance, is really kind of impactful. But then let me also give you a byproduct of this experiment we had, which is understand the driver compliance. Because we send a signal to drivers, say, do this following, and we observe how do they do. So as a byproduct, we observed how much they comply with this. So this says the degree of compliance, right, percent of traffic compliant. You will find that, so this is the deviation from their current schedule, right? The more you deviate from their routine work, the less compliant it is, right? So this not only, we recognize compliance, this gives us a precise measurement of the behavior compliance when artificial intelligence model is injecting the real practice. You can see how people actually practice in this. Right? Now, given this, you can actually improve your initial RL design, which we're trying to do at the moment, right? So now we learned how people will respect or disrespect your decision or recommendation. Can you then preempt this compliance in your initial design? That's what we're trying to work on a little bit. You know? All right, so now we scaled in, did this in Chicago, try to scale it up, also try to kind of outreach to the other US agency to kind of scale up the impact there. Lastly, I will talk a little bit on the creation part, right? You know, on this, let me just describe you that different building environments really impact people's behavior significantly. This is the highline, probably many of you visited. This is today's view, and this. So given the two, of course, this you're more likely to walk, to cycle. This you forget about it. I'm never going to do that, right? So here, the similar thing, the sidewalk, etc. But one thing is important is that the urban density and the energy consumption and CO2 emission have a very the clean curve on this, right? So the lower the density, like U.S. cities, they have a much higher energy consumption than a city like Hong Kong or Tokyo, etc. This, right? But then, so just give you a complete intuition here. This Barcelona versus Atlanta, they have about similar amount of population, and this is the actual size of Atlanta versus Barcelona. This is a huge amount of density difference. And given the density, you have a very different travel behavior, therefore, CO2 emission, right? So therefore, in the planning process, can we generate plans? That's interesting here, right? So the classical urban planning process goes like this. The urban planner will take all sorts of information, zoning, policy, public engagement. Then we say, let's generate some layout. Then given this layout, you will get opinions, feedback, then you come do the feedback. This is a nice loop, but except that this process takes weeks and months, right? Imagine a public engagement process. The planner say, oh, here's the plan for your neighborhood, right? Someone raise their hand and say, oh, can you build a bicycle lane somewhere here? The planner says, oh, great idea, right? Come back 3 months later, I will generate a new plan for you, right? 3 months later, nobody remembered the dialogue, all the momentum lost, right? That's often, so with AI to say, can you use AI to help generate and really expedite this feedback loop significantly, right? So for example, this is a piece of land 35 miles north of downtown Chicago. That if we were to develop it with certain this land use expectations, can you actually do that quickly, right? So this one student, we tried this very hard a few years ago. It's really difficult. Just last year with stable diffusion, the student changes managed to do this in half a year, train the data. Let me show you. But this is showing that given that piece of land, respecting this lake and the geography, then build this residential, commercial, then generated this graphs on this, right? So here we learned this from the OpenStreet data. This is actually pretty widely available. For each piece of land, you have actual code of this is commercial, this is residential, this is industrial. you have this road structure, railway road, etc. So you can put those in, and the satellite, and you can let the machine learn about it, right? So this process is stable diffusion, and then you can do this with a control net by injecting this additional information from the planning domain knowledge in this, right? By doing that, you can actually do a lot of things. You can say, take a description of what you want, and also say, here's the constraint, please respect, and generate something, right? So here you want having a control over the generated pattern. It's not like in DALL-E or Stable Diffusion, give me something, and they give you a lot of things without control. Here, so you have the inject control. The second one is to produce alternative. The third one is to respect existing infrastructure or natural environment. And last one is, can you have a different flavor to it? For example, can you have a Texan flavor of the city versus the Californian flavor of the city, for example, right? So it turns out that these things all can be done. This is by Chenyi, his dissertation work. So this would say that you can specify 40% residential, 15% industrial. You can exactly follow that, right? This alternative design. And you can also say, here's the part of Chicago, respect the river structure, respect the road, etc. Then you can put a river in it. For example, this is before you have river, now you have a river in to redesign it. You can put the railway system, roadway system. So the model can be able to respect those constraints and generate the alternative quite quickly on this, right? And this to say for the similar constraint, etc. This is Chicago flavor, this is Dallas flavor, this is Los Angeles flavor, etc. Right? Yeah. So those things, you'll find that, I mean, from one side, this is great. From the other side, we worry about what's our job, right? That's another different talk on this, yeah. But this is to say that you can really emphasize the planning, the engagement process really significantly on this, right? So as a summary, you can represent, you can predict, you can explain, you can control, you can create, right? But I do want to add one more thing, which is that's also a distinction from the natural system. There are really two different roles of a model in city planning. The first one is actually do the prediction, do the control. But the second distinct function of the model is actually to communicate with the public and communicate with the decision makers, right? This is what we call this communicative planning. This is actually the major function of it, right? Many of the problems, including the prior presented, has a problem that is hard to interpret. So that makes the communicative function of the planning entirely impossible. So that's a major challenge that we have to deal with. And lastly, to say that this is the 5 things AI could do. In the communication, has a lot of challenge, as we have to tackle really the interpretability problem before we can actually have a meaningful communication. And lastly, what is success? I think hopefully will always remain the domain of human judgment on this. Right? Great, thank you, everybody.